All right, y'all, so we're going to be finishing our solid and liquid unit today with something that is not solid and liquid. If you remember, the reason that this clicks time-wise for us is that colligative properties is no longer a part of solids and liquids, which left a void. And back in October, when we did kinetics, I ignored one of the topics. Had we done integrated rate laws at that time, it would have been a fourth lecture, and you're about to see that it's not difficult. But some of y'all really struggled with kinetics already, so had these other equations been thrown in, it just would have added to your plate. So this is going to feel compartmentalized from what we've done so far in this unit, but I don't think that you'll think it is too hard. But we've got to get our heads back in a kinetic mindset. So if I have my dumb little balloon here, we can talk about, well, what would we study or what would we think about in the demo if I were to refer to the kinetics of this reaction?
Wait, what? How did that just start happening? Did you move it?
There's a reaction taking place. If I wanted us to study the kinetics of it, I would be studying the
amount of the ball.
Pressure.
The pressure. The volume.
I don't
remember.
What does the word kinetic even mean?
Movement.
All right, the movement or
chemical reaction.
All right. Oh man. I wish I was recording in the other class when they all knew the answer to that question. But kinetics would look at the rate at which the reaction happens.
The rate
That's
at
basically
which
what I said.
All right.
I
So
I said rate of chemical reaction.
what we want to do is briefly revisit some of the rate law ideas that we did back then.
cocaine.
So that we can remember what the heck it is we're talking about. So let's revisit the beginning of rate laws here.
Rate laws.
Now, if you remember, what we would do when we were writing rate laws in kinetics is the basic setup of the rate law would say that the rate equals, and then there would be a rate constant, which was represented by the letter K. And then all that we looked at from there were the reactants. All right? So what you'll notice in this fake example is that nitrogen monoxide and chlorine must have been the two reactants of the reaction. Now, in order to find the rate, what we would do is we would multiply the rate constant, which is either given to us or we can calculate depending on the situation. We would multiply it by the concentration of each reactant raised to the order. Now, remember, the exponents in these were called orders. Can anybody tell me, where did those orders come from? How did we find those numbers? Not the subscripts.
The exponents.
Those are exponents. The coefficients is what gave it to us. All right? Hey, the coefficients of what, though?
The coefficients of the reactant.
No, it is the reactants, but that's not a safe way to say it. It was the coefficients of the reactants, but where? Not in the reaction. In the slow step. Remember, one of the things that we looked at in kinetics was what was called a mechanism, where we were able to see the intermediate steps of a reaction. And one of them was labeled the slow step. What was the other name for the slow step?
Mechanical.
RDS.
Oh, the rate determining step.
The rate determining step was also known as the slow step. So, what we would do was we would look at the reactants of the slow step, and those coefficients would become the orders. One of the other things that we did was we would draw energy profiles. So just as a reminder, who can tell me a conclusion that we could get out of this energy profile? Somebody shout it out.
The second one is the rate determining step.
All right, so Isaac said that this would be the rate determining step. You're absolutely right. What else could we conclude? that there would be 3 steps. Remember, every hump was a step. So if we had 5 different steps of the mechanism, then the reaction, the energy profile would have 5 humps. Ooh, now, there's not always a catalyst. But Dylan, since you said it, if there was, where would it be? Right there. This would be the only location that I could have a catalyst. Hey, but what would happen if when looking at the mechanism, remember we would cross stuff out? What would happen if something got crossed out at the end of the first step? What would we call him?
Intermediate.
An intermediate. Look at all the stuff some of you remember about kinetics. Why did I didn't even look at you. Why did you act like I was... All right. So this is some of the items that would be pre-knowledge, and we're going to go over all of it again in April when we start preparing for the AP. But this would be the slow step and would help determine the rate law. Now, each reactant at that time would be raised to the power of its own coefficient. But remember, when we wanted to know the order of the entire reaction, we would add up the orders of the individual reactants. So there's my foundation review. I'm sorry?
Can we sing a happy birthday?
Oh, God.
Please?
After the video pauses later, maybe.
Okay.
But I still think she's amazing. Okay. So what is this one topic I left out? It's called the integrated rate law. It's a way that we can say, okay, well, I've got a reaction. I know it's rate law. What if it started at 5 molar and 10 minutes passed? What would the molarity be after the 10 minutes? This is an angle of rate laws, kinetics, that we didn't look at back in the unit. All right? What would the new molarity be after a very specific time? And using the new equations I'm about to show you, you can absolutely find out, which is very helpful in lab. The good news about today is that 2 of the equations I'm going to show you are AP sheet equations. And I always like when those come into play in a lecture, because you know they're asking you questions on this stuff if it's actually a printed equation on the sheet. So we've got 3 different orders that we care about. Now, on your AP sheet, they're only going to be giving you the equation for first and second order reactions. What that should indicate to us is that they won't ask you to calculate a 0 order reaction. But they have. I found it. Therefore, I suggest you memorize this. I'm going to show you a very simple way to memorize this one formula since it's not on the AP sheet, under the assumption that curveballs exist. I don't get to write it. Now, in each of the 0 first and second order reactions, you're going to notice that the variables of the reactions are the same. They're just moved around a little bit. So it's important that you know what the variables are. All right? So my concentration of A is going to refer to just the concentration at a certain time. All right? That's usually the one you're wanting to find out after a certain amount of time has passed in the reaction. The A naught is going to be the initial. So if you go back to my example a few moments ago, I said, what if we start off with 5 molar? Well, that would be the A naught. We started out with 5 molar of whatever it is. I'm wanting to know in 10 minutes, what will the molarity of the reactants be then after they've been converting into products, which is the other A that we would solve for. K is going to be your constant, your rate constant, and then of course T, all of this will be a function of time. One of the things that is very common is going to be for you not to necessarily draw a graph, but for you to connect integrated rate graphs to the different orders. So what I want you to be able to do is know the 3 different graphs and just be able to say, oh, that's second order. All right, oh, that's 0 order based on what I'm looking at. So what you'll notice in my 0 order graph here is that the X and Y axes match units that are found in the equation from the previous slide. Not only that, it's a straight line that is in a negative slope. So it's important that you know that this is always what a zero-order integrated graph will look like. But they might not ask you any zero-order questions. So I'm going to, but they might not. So here's the first of the equations that are on your AP sheet. Now, you'll notice that this has all the same stuff with natural log added to it, but you don't have to memorize that. It's going to give you this. However, if you look on this slide and the previous slide, you'll notice that I rewrite the reactions. I'm sorry, the equations. The reason I'm rewriting them is because since a lot of the integrated rate law stuff connects to analyzing a graph that's a straight line, it makes sense for me to move the equation around to match that straight line. What is the equation for finding slope? All right, y equals mx plus b. What you'll notice is all I'm doing here is basically adding the natural log of naught to the other side to get this equation. But what it does is it turns the information into matching that straight line. Y equals mx plus b. Now, of those letters, which one is slope?
Negative K.
Okay, you're both right. It's m is the slope in y equals mx plus b. And then, as Dylan pointed out, but in chemistry, it's k. Look here. Here's one of the most important things I'm going to say. As I look over multiple choice questions on past AP exams, here's a cute thing that they'll do. They'll give you a problem that's got a lot of information in it. And one of the pieces of info they throw at you is the rate constant. All right? And I'm sorry, I said that backwards. One of the things they throw at you is the slope. They say this is this, and there was this molarity, and the graph had a slope of this, and blah, blah, blah. And then it says, what's the rate constant? And as you start to work out the problem, you'll find that they didn't give you enough numbers to use the equation to find k. What did they want you to do? They wanted you to realize that they gave it to you directly. They called it slope, but slope is k. So don't get tricked there, because in that problem that I'm thinking of, it gave you all the information, and then one of the answer choices exactly matched a number from the problem. All right, it has to be positive, it can't be negative. All right, it's absolute value. But sometimes that y'all are scared of answering that. I've seen from mining test data that if one of the answer choices is one of the given numbers, you just assume it's a distractor. All right, in this case, it's the answer. So I need you to realize that if they give you the slope in any circumstance, that is the rate constant, the absolute value of it. Question? I saw a hand. Yes, always. There's no such thing as a negative k.
Yeah, so, yeah, you say negative K, but it's not.
Because, so based on the number that goes in there, that's going to make it positive. Y'all see what Carolyn's looking at? She's like, but hey, negative k, stupid liar, right? No. But when you pump numbers in there, it's going to make k come out to be positive. Now, the other thing I want to point out is that, hey, look, that looks exactly like the zero-order graph. The only difference is the x and y axes. Do you see how now natural log is a part of the axes, whereas in zero order, it's not? When I say that you should memorize zero order, there's not even really anything to memorize per se. I want you to compare zero order to first order. What is the only difference?
The number.
In the equation, what's the only difference?
The order.
Natural log. Natural log is the only thing. So since the AP sheet is going to give you the first order equation, if you just remove ln from it, you now have the zero order equation. So that's how I memorize it, but just trying to prepare you for any possible thing that can happen. What? I prefer it. That means yes.
Do you want me to sit next to you?
Nope. Okay. Finally, second order reactions is the last one that they will care for you to focus on. And you'll notice it's the only one with a positive slope. So that's important in your recognition of these integrated graphs. Same thing. This is what's going to be on your AP sheet. This is the way I think you should analyze problems because it makes it look like the slope equation.
So K can't be negative, but the slope can be negative, like in the zero and first order.
That's what I'm confused.
Because it's the absolute value. K is the absolute value of the slope.
Is it going to get easier with the problem?
I think so, yeah.
Does that mean the concentration increases?
Say that again.
Does that mean the concentration increases in that type of thing?
That the concentration of the, yeah, but it's 1 over A. Watch, we'll go through a problem. Do you see? It's making 1 being divided by a bigger number.
Yeah, it's gonna make it smaller.
Okay. Me?
No, the board, yes.
Well, I look for the best words before I just jump into. I get asked questions I've never been asked before, so I have to make sure I use everything correct. A half-life comes into play here since time is now a major focus of these equations. So, with time coming into play, first off, the definition's real simple. A half-life is the amount of time it takes for the original concentration of the reactant to drop down to half of that starting value. Simple enough. Here's the really good news about AP. All of the different order reactions have different half-life equations. However, the only order that they'll ask you about is first order. First order reactions are radioactive. First off, all reactions have a half-life, all right? But we're only going to focus on first order reactions because that's all AP will ask about. And the good news is that radioactive reactions, their half-lives do not depend on concentration, which means when we look at the different molarities, the starting molarity or the molarity after 10 minutes, when we're finding the half-life of a reaction and it's first order, which is all we'll look at in here, you never have to look at how much you're starting with. It'll always take the same amount of time to chop whatever that amount is in half, regardless of what the starting molarity is. Even if you didn't understand what I just said, it's fine. All right, I'm just telling you, it's good news. This is so much harder in college.
Awesome.
So there at the bottom, you will see another item on your AP sheet. And it says that the half-life of a first-order reaction is found by dividing 0.693 by the rate constant. But it's given to you. You don't have to memorize anything about that. Are there any questions on the theory before we get into the plug and chug?
Do they ever ask you for like the half-life?
They will. They might say something like, how long will it take for there to be 25% of the original sample? How many half-lives do you have to go through to get to 25%?
9.
2.
So would you just multiply?
I was thinking in cat years.
All right.
So no matter like what, like, you would do that again. All these cases.
Right. Exactly. Yes.
So if you wanted to report it, you would just do 2 with the subsequent 1
Yeah. Maybe. I don't think in those terms. But if you do, then I think you're a wonderful person. All right. So let's take a look at a problem. So I want you to realize that because of the nature of the way that I've taught it in this course, my problems are going to say, hey, this is first order. Now let's do some work. But realize that on the FRQ, since I've trained you previously to find the order yourself using mechanisms and stuff, that it might not always hand you, say, hey, this is second order. And then you're like, oh, well, I'll use the second order equation. You might need to go through the steps I previously taught you, figure out, okay, this is 0 order. So now I know to use this equation. I'm not doing that to you in this unit. But we'll go back over it in April because FRQ style on the real AP will likely do that. What type of kinetics does this reaction follow? Find it. First order. So I know that I'm going to use this equation then.
How did you get that?
It's written in the...
Up here.
Oh.
There's my equation. All right, let's take a look at what we have. First, I'm going to see, do we have a concentration that's later after time has passed? No, we don't. It wants us to find that. So I'm going to leave this just as is because we're trying to find what the concentration is after a certain amount of time has passed. I do have a rate constant of 0.0410. Now, fix this in your slides. They will never give you a 1 sig fig thing. Make the time 10.0, please. That's my bad. I'm sorry. Make the given time 10.0. I just don't want there to only be 1 sig fig in my answer. That's annoying. Times time. And then plus the natural log of the starting molarity, which in this case is 0.2. You can run this into your calculator exactly as is.
Wait, so you're saying we never get a negative. Oh, wait.
Relax, you're not done yet. We don't want the natural log of A, we want A. I get negative 2.02, but we're not done. Are you with me?
Wait.
I'm assuming that means yes. No one said anything.
Yes, we are with you.
You did the negative and the times and the plus and the natural log?
Oh, awesome. Thanks.
Now, here's where we find out who's taken algebra. I need to undo a natural log. If you look at the natural log button on your calculator, the secondary function is the opposite process. And what it is it's e to the power of. And in this case, negative 2.02.
I thought that we were done with that.
Yeah, you said you weren't doing that, but okay,
And I get 0.133 molar. So check it out, but it's nice to know what you can take out of this. It means if you were going to do this reaction and start with 0.2 molar, all right, then 10 minutes later, that's what your molarity would be of your reactants. Hey, are we allowed to try to find the half-life of this reaction or no?
Yes.
Why are we allowed to? Because it's first order. All right, so then what do we do? If we take a look, I know that the half-life is equal to 0.693 over K.
Wait a minute, where'd you get 0.693?
It's a constant value that'll be printed on your AP sheet.
Oh, thank you, sir.
Therefore, this is so simple. What do I do?
0.693
Divided by what?
0.0410.
Perfect.
10. I got it right? Period.
The rate constant was already in the problem. And now we can find out exactly how long must this reaction run before we only have half of the H2O2 left. How long is it going to run for?
What unit?
1.69.
No.
16. Okay. I put an extra 0. My bad.
It's a min. Yeah, well, I mean, if you go back to the problem, your rate constant was in minutes.
Oh, so it'll be based off of...
Oh, yeah. Oh, yeah. Because it could be in seconds, depending on how the problem's given.
But I'm losing so many points on effort already. I will put second.
Count it from right here. Whenever you actually do the effort.
What do you think? Let's do another one.
Hold on.
Somebody find the primary or the biggest difference in this new problem.
That's gas.
Oh, it's second order.
The other one had gas. Yummy.
Well, second order has a different equation that's also given on your AP sheet. Can we find the half-life of this when we're done? No. You can, but we are not required to at any time in AP. So we're not going to mess with it. And it's a funky equation to do it. Funkier. Yeah.
I have right here, it says in the previous problem, how long would it take for H2?
Yeah, I altered it. Yeah, did y'all see that I had to edit in that last one? So half of.
Well, she wrote in pen, so she can't alter it.
I'm sorry.
All of the first orders are radioactive?
All first order reactions are radioactive, and all radioactive reactions use 0.693 over K.
Really?
Okay. Uh-oh, second order. This isn't any fun. Let's first put our equation up here. Notice that there is not a negative this time in front of your K. There doesn't have to be because this has a positive slope already. I'm sorry?
Oh my gosh.
Do I have whiteout? Maybe. I'll go look.
Yeah, I know.
Just rewrite the whole page.
Hey, brother.
All right, so here we go. Hey, look. It wants to know what will the concentration be after time has passed. So the same variable is missing. So I'm going to leave him just like that. And now we can start inputting the values that we do know. The rate constant this time is 5.76 e negative 2. 5.76 e negative 2. All right. It's 10 minutes again. This time it's written correctly. All right. Plus 1 over the starting concentration of 0.2. The 11. All right, so let's simplify. You can type all of that into a single function on your calculator. Do you get 5.58?
I didn't get that.
You bring your own, but you can't use it on the multiple choice.
You can't?
You have to use number sense for a lot of it. I'm going to help you with that in April. But a lot of times the
So much fun.
answer choices will be unsolved work. Like it'll end up looking something like this, and just pick which one inputs it correctly.
Oh, that sucks.
It's stupid. I don't get it.
Am I doing something wrong if it only gives me 2 past the decimal? Because I got 5.57, and so I wouldn't have known to round it to 8.
So aggressive.
I know.
I don't know why I'm doing that.
You might be able to do like math.
Oh no. You went 5.70. It's 5.76.
Oh my god, I can't.
See whose fault it is? Okay. Now, solving from here is simple. Based on the questions that y'all asked me on Schoology a lot, I think y'all benefit by looking at it like that. But if you don't need to, then just solve. It's algebra. All right? But if you cross multiply, it ends up being 5.58a equals 1. So then how will we solve for a? Divide by 5.58.
Why would you put the A next to it?
Because I cross multiplied.
Okay, cool.
You use the belly of the
Curiosity.
factors? Interesting.
That's kind of weird.
No, he does the belly of the 5 first whenever he's drawing a 5.
Like he goes like down and then like.
Like, he'll go like this. He goes like
He writes
this.
better on paper than
I
he
don't know,
does.
he
He
goes
goes up. He
I
doesn't
don't
go
know,
down.
you draw 5.
Wait, draw 5.
Draw 5.
That's how I do my
No,
fives.
see, he goes down.
You're so weird.
I don't know. I don't trust it.
I go.
It's easier to
How do I
See
draw
if you get my molarity.
They don't even
I go
connect.
from the head.
That keeps it from breaking like an
But
X.
just draw the tail.
It's very easy not to make it.
No, I draw the line, I draw his curved leg, and then I put a
It's supposed
stupid
to be
hat on.
Factor of 5 is
not
that it
two.
has.
See when I
Yeah.
go like this?
No.
I think he does it so it doesn't look like an S though.
But there's a distinguishing feature of a 5
Like,
and that
draw-
it
draw
has
it-
a
draw it-
direct right angle within it.
What?
Are you
And then you
okay?
do the curve.
Draw it like one motion. Yes. Draw it like one motion.
I don't want to do this.
Unlawful.
See, that's so much better.
It looks
I swear if you clap for a 5 one more time, you're all fired.
The other fives look
You
fine.
see how it's straight and the
I-
other one's not? It's like how you're going.
No, those
Inspired.
fives on the bottom are
they're
nice.
so curvy.
Fire has a
Ooh.
All right, you try one. Last problem of the lecture of the unit. Can you figure one out without me?
Okay,
No.
you dig it.
Call me over if you get stuck.
Watching the videos from like your previous classes is so sad. When the classes didn't have personality.
Or he threatened them into silence.
Like they never say anything.
Yes.
Like, every once in a while somebody will.
Probably had like a whole collection of katanas right on the outside of the screen, hidden from view.
Here, do the work instead of
The door.
Are we done?
Yeah. People are bettering themselves right now.
Yeah.
Well, you need to follow order of operations. Step by step.
The last time I saw it, I laughed through it straight 4 class periods.
I don't worry about
Every single time I found it, be that. Did nothing. It just made it harder to see the question.
A naught is what we started with, and A is the one that it changed to. So which one did they start with? Well, you wrote it down. You don't have to repeat it.
Current is the back.
Current is the
Pope Francis said J after supporting coronavirus sufferers.
Wait, what?
The coronavirus sufferers.
It says did you ever into your phone? What? You go from
Wait,
you have your wife in your phone and there is
How stupid do you feel about it?
That's.
You know what I have tonight? I have this daddy daughter dance.
Yo, we, it sounds like
He's on their side.
yeah, the daddy daughter dance. It's steel.
Steel.
I think his side.
Who goes to steal?
Yeah.
She's actually
accelerated.
Yeah, but you have to. Meetings there.
Cummings. I mean, she probably did.
No, that's good, but you're divided by negative 100, not 100. It's perfect. You did it perfect.
I just changed it.
Okay, well that's good too. Yeah, if you know it, because what are you finding here? Are you finding the rate? But you're finding the rate constant. Yeah, so you know it's absolutely valuable.
Do you mow the grass with those shoes?
I have before. Yeah.
Why are you calling me out for it?
I'm just questioning. I just saw the.
I think that you should get a Columbia.
Yeah.
Mow the grass in
I
here.
think you should keep your
No,
We'll just talk
North
about that
Face.
later.
North Face. North Face.
A jacket.
North Face would be better.
Is that your jacket?
Yes.
You guys have never seen that.
No, I wasn't there like
It
that.
says Saga Sword and Domestic on the back.
Show you where your non-grass cutting shirt.
What's my way?
Sure, take off the jacket. Take off the jacket, please.
Wait, I need your help.
No, I'm taking off my jacket right now.
You look like the type to go to Comic-Con.
Probably does.
Oh, God.
Yeah. This is the moment. 37:35 in the video. 37:35.
Let me hold up 37.
37:35.
35.
I think I've seen you in a t-shirt. Have you ever worn a t-shirt?
Yeah.
Without a jacket?
He's posing for it now.
Yeah, he's one of
This isn't really posing. This is me just standing.
He's
stood there
definitely
really-
posing.
This is me just standing.
Why do
What was your question?
Leaning back.
Did you still have one?
Why do you have the green
It's
lantern?
Star Wars.
on?
It's Star Wars periodic table.
I saw somebody wearing that shirt today.
You look extra
It was
skinny.
him.
It's him.
No, it was somebody else.
In the green
Well,
lantern.
you don't know this. I want you to calculate the rate.
Zuckus.
So you don't know.
No.
So you do it at the time.
You remember?
Find the time.
No.
What is the
You have a
what is
green-
the temperature have to do with what?
No, she has a green lantern. You can shoot lasers.
You look the type to go to Comic-Con.
All right, let's see how you did.
Shoot the lasers. I heard he can shoot lasers from his eye.
Oh my gosh, it's a Star Wars.
Hey, check it out. It is first order. Hey, we could find Half-Life, but we're not going to. So I'm going to use the equation LNA is going to equal negative KT plus LNA naught. We're going to plug in some numbers. Hey, I've got everything but K this time. So we're going to go ln, natural log of the later concentration after time has passed of 1.02 e negative 3. All right. Is equal to negative KT, or K times 100 plus the natural log of my starting concentration, which is 1.25 e negative 3. Yes?
Can't you use it the way it's written originally? Because doesn't that make it easier? Because it's like that minus that.
Yes, you absolutely can.
Because that's what I did. Sorry.
Her question was, can you solve without converting it to this y equals mx plus b format? Absolutely. This is just how I do it. Sorry if it annoys anybody.
You have to end up moving it.
I'm so annoyed.
All right. So we're solving for k here by using simple algebra. Somebody want to share their answer?
Oh, 0.00203. 0.00203. Let me do it. Oh my gosh.
Is that what you got?
Heaven forbid.
I don't like doing
I don't either.
opening zeros. It's annoying.
I don't like counting.
I like putting what my calculator gave me on the paper.
We have so much in common. I like
To find the half-life, we would do what with that number?
Divided by
the point.
We already did
No, that number divided by that.
0.693 divided by that would tell you how long
Yeah.
half of the sample would last. Y'all have a great weekend.
No, you.
Oh.
Today's Friday?
Hey, we're gonna sing happy birthday on the count of 3. Ready? Come on.
1, 2, 3.
Happy birthday.